Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the trichloroacetamidets and how that trichloroacetamidate is used by using the concept of donor acceptor concept, glycosylic formation or glycosyl bond formation of donor acceptor concept by taking as a some of the suitable example of trichloroacetamidate we have discussed. I think near about 4 schemes we have considered, we have discussed with their stereochemical aspect, how we are anonymously getting as a or exclusively getting as only those products, that is a anomeric controlled reaction. Why we are getting only one? What are the reagent? What is the reaction condition used here? And how trichloroacetamidate can be used as a donor or acceptor, that type. How glycosides are formed, that type of the thing we have discussed in our previous lectures. So today what we are going to discuss is again one of the very prominent or the important point, that is a glycal and glycal derivative. Next point we are discussing now is a glycals and glycals and glycal derivatives. This is a point which we are going to discuss right now. So what does it mean? Glycals and the glycal derivative it means what? How it is useful? Whether is it are they act as a donor or acceptor, or both role they are playing, that type of the concept we are discussing right now. Here iterative assembly of glycals and glycals derivative, the synthesis of glycosylated natural products and complex oligosaccharides. And as we know that at the beginning we have learned while studying as a carbohydrate, classification of carbohydrate are mainly classified into 3 subtypes. Number 1 is a monosaccharide, oligosaccharide and polysaccharides. These are the main classification of that, and among that we are talking about here is a B point, that is a glycosidic synthesis. So far we have learned one is a trichloroacetamidets. So now is a glycals and the glycal derivative. Glycals and the glycal derivative, what does it mean and what type of the thing it is providing, and how to remember, how it is easiest, or how it can act as a donor or the acceptor, that type of the thing we are discussing right now. That is a polypeptide. Have you heard about polypeptide? Peptide, what kind of the polypeptide? During that protection and the deprotection, you come across this word peptide bond. How the peptide bonds means, that is amide bonds are formed while synthesis or while the in case of the protein, there you might have heard this word. So that is poly means many unit combined together through the peptide bond. So that type of the word is called as a polypeptides. Oligosaccharides. Saccharide is nothing but as a sugar unit, remember here. Oligosaccharide and oligosaccharide and the are three classes of oligomers, and that play key role in the transacting the processes of life, while the functions of protein and DNA, protein and the DNA, they has a very close relationship where we are going to study in detail, and that is playing very important role here. Deoxynucleoacid have been appreciated at least qualitatively for over 50 years, and basic information as to the vital mission of the carbohydrate beyond that of energy storage are still being elucidated. Thus, the roles of oligosaccharides in cellular adhesion, protein folding, cell signaling, fertilization, pathogen binding, and inflammation have been recognized only recently. The detection, purification, and structure determination of complex oligosaccharide have been critical in the emergence of glycobiology. The continuing maturation of this science has added to the incentives for preparing complex oligosaccharide conjugates in homogeneous form. Among these incentives is the possibility of evaluating vaccines comprised of synthetic cell-free carbohydrate and based tumor antigens for enhancing immune response to cancers which bear such cell surface epitopes. In addition to the necessity for such a homogeneous constant contracts, the preparation of complex oligosaccharide poses no small challenge to the science of chemical synthesis, while the successes achieved in oligosaccharides and oligopeptide synthesis arose only after long-term and exacting research. The issues associated with oligosaccharides synthesis are of much higher level of complexity. In assembling either amide bonds for polypeptide construction or internucleotide phosphate bonds in DNA deoxyribonucleic acid synthesis, no new stereochemical issues are encountered or recognized, and by contrast each glycosylation reaction in oligosaccharide construction involve a question of stereochemical outcome at the anomeric site alpha or beta linkage, which is shown in the figure. Let us see here how the oligopeptides are formed here. Oligopeptide, how the oligopeptide bonds are formed. Let us look at here. It is a partial structure. I am trying to draw over here NH. Then there will be this junction where the R group projecting above the plane, and then there will be this type of the group, that is a carbonyl group, and then NH, that type of the group, as we know that. And then let us see over here the group which going, that R group is below the plane, and then next one will be C double bond O. Then you can write, this is a structure. If you observe this structure carefully, what do you observe here? Look at this. What is this? This is nothing but as a peptide bond, right? This is nothing but as a peptide bond. Remember, this is a peptide bond, and which is mainly occur in protein synthesis, or this peptide bond is nothing but two amino acids joined together through, there are C terminal and N terminal, as we know that. There are 20 different amino acids, and as we know that general structure of amino acid is RNH2 carbon atom and COH. Most of them are optically active in nature, except glycine. Glycine is only as optically inactive in nature, because there is a two hydrogen group are same, and that's why it shows the optical inactiveness. And rest of the 19 naturally occurring amino acids are found to be optically active in nature, because they exhibit the chiral center. And as we know that generally those organic compounds containing chiral center are found to be optically active in nature. If only as a one chiral center, they definitely exhibit or definitely shows the optical activity. If more than two chiral centers are there, then there are some criteria, or let us say some of the plane of symmetry, center of symmetry, or alternative axis of symmetry. If these kind of the symmetries are present in those molecule, they exhibit or they shows optically active in nature. And those compound, if they possess chiral center more than two, and they don't have such kind of plane of such kind of symmetries is not present over there, like as a plane of symmetry, alternative axis of symmetry, or the center of symmetry, they definitely shows the optical activity. And that's why, remember, there two groups are present in the amino acid. One is a carboxylic group, another one is a amine group, NH2 group. Both are in the same, they attach to the same carbon atom, and therefore it is known as a alpha amino acids. And alpha amino acid, when two alpha amino acid come together and form as a bond. That bond is known as a peptide bond. Carbon nitrogen bond, that is adjacent to the carbonyl group. So that type of the bond is known as a peptide bond, and you can observe these peptide bonds in the protein synthesis or in the protein molecule. So that is a oligopeptides over here. Now second one is a oligonucleotides. Now it's the second one is a oligonucleotides. Nucleotides are that you might be knowing as a nucleides, right? Nucleides means what? Nucleides means there are two compounds are joined together. There is no phosphate involved. Phosphate bond is not involved in that. That type of the thing is called as a nucleosides. And nucleotides means what? There is a peptide bond is observed, and that's why we can call it as a oligonucleotides. And this type of the concept we already studied while discussing or while studying the protection and the deprotection in section number 1. So let's see here oligonucleotide. We can draw here like this. This is a structure of here. I am showing here B1 represent is a base over here, base 1, and here I have shown this oxygen atom, and then further with this one another, it is attached to another nucleosides. So let us see over here, this is the oxygen atom, and then there will be phosphorus O minus, then here once again O, then we can show over here another this type of the compound, then here B2 you can I have shown over here, then O, then P double bond O minus, once again there will be, remember here is another bond linkage is there, but the bond is formed between P and oxygen. It is known as PO, means this is a phosphate bond. This is nothing but as a phosphate bond. This is nothing but as a phosphate bond is observed in this oligonucleotide when it formed. That is a phosphate bond is shown over here. B1 and B2 represent as a base number 1 and base number 2. As we know that there are different type of the bases are there. One is here 6-membered ring, as well as heterocyclic bases are there, that uracil, then thymine. So that are the sum of the bases, and which we already learned in our previous lecture. Then next one is oligosaccharides. Now this is about the phosphate bond. Here we observed phosphate bond. Now this in a third point we are doing oligosaccharides. In a oligosaccharide, how we can show this? Oligosaccharides, and that in the oligosaccharide we can represent this 6-membered ring like this. So here we can show oxygen atom over here, then dash again one more. Here we can write ROP, we can RO, then this side oxygen joined to next 6 membered ring, which is shown like this. Again it is further joined to another group. Here you can show OR, here also as OR, here RO, here OR, all are the protected hydroxyl groups are shown there, and the bond is formed here. This bond is nothing but it has a special name, is a glycoside bond. This is nothing but as a glycoside bond. This is a glycosidic bond, glycoside bond, and this figure represent, this is the figure number 1 over here. Remember this one. This is a figure number 1 where I have shown here oligopeptide bond, how it is represented. You can clearly observe over here. Then second one is a oligonucleotide. Oligonucleotide, the 5-member furanose type of the structures are so shown over here, and there you can observe there is a phosphate bond. How that phosphate bond is formed among this deoxyribonucleic type of the acids. Then oligosaccharides, where you can observe the glycoside bonds, how it is formed and how the others are formed, others thing remains over there, and we have seen this one, that is figure number 1, alpha and beta linkages we have seen. And moreover, every glycosylation event require identification of a specific hydroxyl group to serve as an acceptor center, that is a scheme number 1A is shown over here, and that scheme number we will see here. But before that, let us see some of the description regarding this. In a typical hexose, the pinpointing of an acceptor site obliques one to identify one of the 5 potential hydroxyl group to serve as reaction locus for glycosylation, reaction focus for glycosylation. In some instances, these specificity or selectivity of action may reflect inherent reactivity margins between free hydroxyl groups. Alternatively, and much more commonly, oligosaccharides construction involve extensive reliance on the use of protecting group strategies for purposes of reinteraction of specific protecting group at the reducing in and of an oligosaccharide having been brought in at the glycosyl acceptor stage would then be converted into or donating group. In addition to the requirement for manipulating the acceptor and donor character of the terminal hexose with each elongation cycle, the need for inclusion of N-acetyl function as well as occasional C-methyl, O-methyl C-acyl or O-acyl or sulfated alcohol group, not to speak of sialic acid unit, serve to further complicate an already daunting set of challenging, and it was with the consideration in mind that we began to explore the possible advantages of a new strategy, that is glycol assembly to facilitate oligosaccharide construction, while the use of glycols as direct glycosyl donor or precursor of glycosyl donors had been practiced long before our entry to the field in 1988, and it seemed that several potentially interesting and promising synthetic opportunities had not been recognized. Upon casual inspection, it appeared that the complexities associated with differential hydroxyl protection would be significantly reduced in a glycol. Thus, in a hexose glycol, only 3 hydroxyls need be distinguished. Scheme number B. Further, that is shown. Let me show you the scheme number A and scheme number second. Let us see what are those and how we can know the glycols and the glycols derivatives, how we are getting over here. Let's see this one. So here, suppose as let me show over here the A, where the 6-membered ring we can represent like this. So here O, and this side you can write, or not, here we can write as a H over there, H. Then other side all are the hydroxyl group, OH, OH, OH and HO, right? This is one of the compound, and then this carried out this reaction in a many step. You will arrive at the structure number this. Here you can show X, then here PO phosphate, then PO, here also you can write PO, here also we can write as a OP or PO, right? And then another way, in the same way, if you take as a this compound once again like this hydroxy group, then this is a ring structure of glucose I am showing here there, OH, and again doing so many steps by protection. What do you get? You can get this compound in such a way that here OP, then everywhere is a OP, OP, here PO, then we are kept as a hydroxyl group, one is free, so that this X and this hydroxyl group get combined together, and the resulting compound formed will be this one. This is a compound which we are going to get over here like this. Here O, not like this. Here we can show this compound like this. Here maybe as a, what is that, OP, this compound, OP, then PO. Here this compound, it remains as it is, PO, then PO, OP and OP we can write like this. So this is the compound which we get over there, and after that if you carry out this reaction some other way around and many step, what do you get? You are going to get the compound here will be this one. Again 6-membered ring you can write as it is here, the 6-membered ring, where this OP is converted into as X, other thing OP remains as it is, PO, here OP, then PO, and this also remains as a PO as it is, right? PO, and then it will be treated with some other reagent, some other compound like this one, same, which one? This one. If combined with this, if you treat with this compound, OP, then OP, and here is a PO, then this compound, hydroxy group, then and then you are going to get finally this is a oligosaccharide. What you are going to get here? Oligosaccharide. This is the point you are going to get. This is the compound you are going to get. Observe this A carefully. What we have taken over here. Look at here. This one. This is one of the ring compound. Pyranose type of the compound, this and this, doing many steps over there, and we can protect selectively this hydroxy open, and so this and this get reacted, we are getting this one, and by deprotecting some group so that we get X over there, and this further treated with the same reagent, and we are going to get as a oligosaccharide. So that is there. Another way which we are going to get is the B side over there. So let's see how this is going to get that one. I think we have seen this compound, how we are getting this one. Let us see the B scheme over here, how we are getting as a B glycal's derivative, how we are getting as a derivative, that we are talking for it. Oligosaccharide, how the oligosaccharide derivative obtained, that we have seen. In the next way, we are going to see over here double bond, then here is a RO, right? RO, PO, not RO, PO. First PO, then PO, then again PO. So that are the 3 bonds are there, and then it will be treated with electrophile. So electrophile is going to add either this side or this side. It is definitely is going to add either this side. So away from the oxygen atom, and so that electrophile and another compound of this one. This compound we are treating double bond, then PO, then here is a HO. This is a free. Electrophile is going to add over there, and this linkage is going to add over there, and so you will end up with this one. So this as it is, then PO as it is, PO here should be E, and then this oxygen, and then combine we are going to get this compound over here. Once again, here is a PO, here also as a PO. Then here you can write this one, double bond remains as it is because we are treating with this compound. If you observe this carefully, how the reaction takes place, electrophile generated over there, positive charge over there, and therefore this positive charge can attack this OH can attack over there, and this double bond is attacking, and we are getting as a this type of the compound. And once you add here is a electrophile and this reagent, once again what you are going to get, it is a PO, here PO, then this compound hydroxyl group, what you are going to get, once again this type of the combination you are going to get. Once again this one O, this, so electrophile is here, oxygen, then here you are going to get this one, here electrophile, once oxygen atom, and then again O there, this one double bond, here is a PO, here also as a PO, here PO, here also as a PO, here PO, here also as a PO, and here you will get as a PO. This type of the compound you are going to go on getting that derivatives, and that is again there you reiterate what you are going to get is a oligosaccharide. Reiterate. So what you will get here, oligosaccharides. So in this way we have seen how we are getting as a this one. We have seen over here, so more each hydroxyl could well differ from each other. So in this way we have seen how the glycose and the glycal derivatives are obtained over there. So with the help of two examples we have derived that glycal and the glycal derivatives. I think with this let us stop today here. Remaining we will see in the next time. Thank you. Have a nice day.